Welcome to the first of 3 videos where we're going to explore the physics of music. And in particular, we're going to examine what allows any instrument to produce music, whether that's an organ or a piano or guitar. How do musical instruments produce music? Now, all sound relies on sound waves. So in this video, we're going to focus on a basic introduction to waves. So we begin with a very simple question. What is a wave? Now, a wave is simply a transfer of energy through some medium. So let's take a look at a more common, concrete example that I'm sure you're all familiar with, and that is the idea of a wave through water. So if we have a faucet dripping into a tub, the droplets of water will cause a cascade of waves through the pool of water. And what you see here in the lighter areas are the crests of the waves, and the darker areas, as you're looking down, represent the troughs of those waves. We can also look at it side on. And again, you can see here as the water droplets drop into the pool, the energy from those droplets cause a wave within the pool of water, and that energy is carried through the rest of the pool, causing the waves. So now that we have a basic definition of what is a wave, you just have to remember that it's simply the transfer of energy through some medium. We're going to take a quick look, a closer look rather, at a particular waveform and discuss some of the vocabulary that we can use to describe waves so that we can compare them. So here we have a close-up of one full wave cycle. So again, we'll put this in concrete terms, and we'll imagine that you're standing in the ocean as the waves gently roll in and pass you. One of the first things that you might notice standing there is how high are the waves. So we'll measure that relative to what the water depth would be if there were no waves at all. So that's what we call this midline here. And the height of each crest, or the depth of each trough, is what we refer to as the amplitude. So if someone asks you to find the amplitude of a wave, what you're looking for is the maximum displacement from the midline. And in this case, for this particular wave, that's 1 centimeter. Okay, shown here in red. So you have a wave that's coming in that has an amplitude of 1 centimeter. All right. In addition to looking at the height of the wave, we could also ask, how long does it take for one full wave to pass us? And that is something that we refer to as the period. So the period of the wave is how long it takes for one full wave cycle to go by. All right. And again, looking at this particular wave, we can see, looking at the x-axis here, which is given in seconds, it takes a full 18 seconds for the wave to go by and the next one to come in. So the period, which we refer to as t, is equal to 18 seconds for this particular wave. How long does it take one wave to go by, is how many waves go by in 1 second. All right? And that would be what we refer to as the frequency. So the frequency is how many waves pass in 1 second. And you can see on this particular wave, we don't even have a full wave that goes by in 1 second. We have a fraction of a wave that goes by in 1 second. So the period was how many seconds per wave. Now we're going to look at the reciprocal of that, how many waves per second. So the frequency is always the inverse of the period. So in this case, our period was 18 seconds, and so our frequency is 1/18 of a second. In 1 second, only 1/18 of this entire wave has gone by. And of course we can convert this fraction into a decimal, and the frequency is given as 0.056 or 56 thousandths hertz. Hertz is inverse seconds, all right? Frequency is always given in hertz, or almost always anyway. And a hertz is a unit that is simply inverse seconds. It's cycles per second. So for this wave, the frequency is 1/18th of a second, or 1/18th hertz, or 56 thousandths hertz. All right. Finally, one other thing that we could discuss, which isn't shown on this particular graph, is how long does it, or what is the distance rather between one wave and the next? And that would be what is known as the wavelength. Now that isn't plotted here because what we've plotted on this particular graph is the height versus the time. So standing on the shore watching the waves come in, how long does it take for the crests to arrive? All right. So now let's take a look at a few examples and get some practice finding the amplitude, the period, and the frequency of a few different waves. So here we show two different waves, one in red and one in blue. Again, our y-axis shows the height in centimeters, and our x-axis plots the time in seconds, so how long it takes for each wave to roll in. And we'll look at the red wave first. The amplitude here, remember that's the distance between the midline and the peak of the crest, or the depth of the trough. The amplitude for this particular wave would be 3 centimeters. The period, again, is how long does it take one complete wave cycle to go by. That's again going to be 18 seconds. All right, which means that our frequency, which is 1 over the period, is 1/18th of a second, or 1/18th hertz rather. So 1/18th of a cycle goes by every second, or again, that 56 thousandths of a hertz. And then we can also look at these values for the blue wave. The blue wave here only has an amplitude of 1 centimeter, but the period is that same 18 seconds. It takes exactly the same amount of time for one full wave to go by as it does the red wave. And so the period is again 18 seconds, and the frequency is 1/18th of a hertz, 1/18th hertz. All right. We can look at one more example here. We have a yellow wave. So here our amplitude is going to be only 2 centimeters because that's the maximum distance between the midline and the crest. And now our period, so again, our period is how long does it take one full waveform to go by? Well, it's a little hard to read on this graph because it's not broken into, the x-axis isn't broken into small enough sections to be able to precisely read the period, but we can see it's going to be around 3.5 seconds, but there's a better way to calculate it. So what we can do is we can see that in 18 seconds we have 1, 2, 3, 4, 5 complete cycles. So in 18 seconds, I have 5 full cycles. So I can calculate the period of one cycle by doing the calculation 18 seconds for every 5 cycles. I divide 18 by 5, and I get a period then of 3.6 seconds. All right? So which corresponds with our initial estimate, which was about 3.5 seconds, right? One full period is 3.6 seconds. And our frequency then is how many waves or what fraction of a wave goes by in 1 second. I can take the inverse of my period and get 278 thousandths hertz. So here's one final example to wrap this video up. I'd like you to pause the video and take a look at the wave presented here and try to calculate the amplitude, its period, and its frequency. Once you've done that, you can play the rest of the video and we'll go through it together. So for the amplitude, you should have calculated simply the maximum height between the midline and the crest of the wave, which is, for this particular wave, 3 centimeters. Our period, which is how long does it take for one wave cycle to complete, that's pretty easy to read off this particular wave. It's 6 seconds. And the frequency, which is always the inverse of the period, calculates how much of a wave goes by each second, is simply 1 over 6 seconds, or 167 thousandths hertz. So that concludes this introduction to waves. Please visit discoveryquests.com to find the other 2 videos in this series. In part 2, I'll be discussing sound waves, and in part 3, we'll look at sound waves within musical instruments. You can also visit discoveryquests.com for additional lesson plans and project ideas. Thank you.